So if we double the acidity, let's say I start with an H plus concentration of 1 times 10 to the negative 5. With your calculator, take a negative log of that, and you get 5. If we double the acidity, it just goes down to 4.7. Again, pH units are logarithmic, so they're not linear. Everything's base 10. Logarithms are used a lot in science because you can take a sigmoidal curve and make a linear curve out of it. And people are just, when you look at a curvy line, people can't analyze that. It's just not a skill for people. But if you make it into a straight line, that you can compare with other straight lines and make sense of it. And so we use logarithms a lot in science to take a curvy line and make it into a straight line so you can glance at it and make some comparisons from it.
So for,
Yeah?
oh, what was it? So whenever there is more acidity, then the pH is always lower?
Yes. The more acidic, the lower the pH goes. So like 7 is neutral, 6 is a little acidic, 5, 4, now you're in tomato juice territory, 3, you're in orange juice territory, 2, you're in lemon juice territory, 1, you're in stomach acid territory, 0, now we're just in chemistry lab territory. That's a 1 molar solution. -1, now we're at a 10 molar. That's basically concentrated hydrochloric acid.
Oh, yeah.
And then more specialty chemicals might get to -2 or -3. But yeah, the lower it goes from 7, even into the negatives, the more acidic it's getting.
How negative do you go?
There's no limit.
So instant, so some of the most acidic things touch your skin and all burns instantly. Just eat it.
Maybe. Let's find out.
Oh man, I don't want to tell you nasty.
I mean, solvent buffers acidity. So like, let's say I put triflic acid into water. That's way more acidic. But the first thing it's going to do is donate its proton to an H2O. And so what I really have is H3O+. And so in any system, the solvent moderates acidity. But if I was in a different solvent, like diethyl ether, now I might actually go a lot more acidic. So what is the most acidic thing ever? Fluoroantimonic acid.
Okay.
I wonder what the pH of that is. I don't know. It's so acidic, it's not using pHs. But it is 20 quintillion times stronger than pure sulfuric acid, which is...
Does that tell you something?
I don't even know what the pH of that would be.
We'll look up one
All right.
pH balance of lead. Figure it out. -18.
-18 has been achieved.
Okay. I don't know. That's maybe not it.
Huh.
So wait, if you start mixing acids with acids, do you get more deadly acids?
Yeah, like chemists learn how to make fuming nitric acid and fuming sulfuric acid.
Yeah.
Those are so unstable you can't buy them. You have to make them in your lab. But yeah, you could make fuming. Some recipes do call for those specifically, and you can't skimp out on that. You can't just use normal nitric acid. You really do need to use fuming nitric acid
What do you
then.
hold that in?
A glass vial, and you use it, and then when you're done, you destroy it.
So glass, a high acid will not eat glass or like go through glass.
Hydrofluoric acid is the only thing that eats glass in the chem lab.
So then what, okay, so if you want to mix,
Hydrofluoric comes in wax bottles.
okay, so if you want to start mixing acids, and what would be, if you didn't know what it eats through, what would be the best thing to put them in then?
Glass. I mean, you would know if you're using hydrofluoric acid.
Yeah.
You should, because it's dangerous. So like, not knowing would be irresponsible because of how dangerous it is. So yeah, that's why everything in chemistry is glass. Glass is really inert. Not much reacts with glass. The only reason hydrofluoric reacts with glass is because the only thing that silicon likes more in the universe than oxygen is fluorine. So it will only let go of its oxygen buddies in glass if you give it a fluorine to grab onto. And that's why that's the only one that works. So negative 18, which is pretty acidic. And there's no good way to even compare that.
Use that for? What would you even use that for?
You're doing.
And was like, oh, I'm going to create this.
You're doing industrial chemistry at that point, like and you probably your solvent's not water at that point because that'd be a waste.
What would you use for? Like,
For some chemical reaction, probably.
oh, so it's just good for what, blowing things up?
No, like for synthesizing molecules.
Oh my gosh, that's way too advanced for no. That's crazy. There's like,
I mean, if you work it all the way back, everything you see comes from some very basic resources. People grow plants, you get plant fibers like cotton. People grow trees, you get wood. People pump oil out of the ground and can make chemicals out of your starting mixture of your oil bases.
yeah.
They mine metals, so you have metals to work with. And then from that, there's layers and layers of industry which keep making more and more complicated chemicals that result in the infrastructure that can make products like that pop in that bottle and that computer and stuff. But it all starts from almost nothing. It has to work its way up each different level. And so like a lot of chemical factories these days are like in China and stuff, and like a whole factory would just make sulfuric acid. That's all they made. Or a whole factory would just make titanium dioxide, and that's all they made. And so you're making these raw materials that then other companies can use to make things that you might buy on the shelf or something. So it'd be one of the industrial states that you would need that. All right, give me a pH of a solution of 0.015 molar H3O positive. We're going to take a negative logarithm of 0.015 molar, and we get 1.8. What is the pH of a 0.020 molar hydrochloric acid solution? Again, that'll dissociate into H plus and Cl minus, but it's 1 to 1. So in solution, this would be 0.02 H plus. So we take a negative logarithm of 0.02, and we get 1.7 for the pH, which is pretty acidic, more acidic than pure lemon juice. What is the pH of a sodium hydroxide solution with an OH concentration of 2.5 times 10 to the negative 11? Well, it's a trick question because they want the pH. pH is negative log of H plus. They didn't give you that. But you do remember that the H plus times the OH minus is always equal to 1 times 10 to the minus 14, always. And so we're going to first find the H plus concentration with that knowledge. So we divide 1 times 10 to the negative 14 by the OH concentration to get the H plus concentration. And now we take the negative log of that to get the pH of 3.4. If you just take the negative logarithm of the hydroxide concentration, that's the POH, not the pH. The pH is the negative log of the hydrogen concentration. Neutralization. An acid and a base react to form a salt and water. When we write an overall ionic equation, all the aqueous compounds are broken apart into their ions if they are strong electrolytes. Weak electrolytes are held together because, like acetic acid, 95% of it stays together, so it's more accurate to write it in its molecular form. But the strong acids, the strong bases, and the soluble salts will be broken apart into their ions. And so HCl aqueous becomes H plus and Cl minus aqueous. Sodium hydroxide aqueous becomes Na plus and OH minus aqueous. Then that forms sodium plus and chloride minus aqueous, and then water. And then to get a net ionic equation, we cancel out the spectator ions. Anything that you find on both sides of the arrow, like this Cl minus is on both sides just hanging out, and this sodium is on both sides just hanging out, we cancel them out. They're called spectator ions because they're not doing anything, they're just watching what's happening. What really happened was H plus combined with OH minus to form water. And the Na plus and the Cl minus were there at the beginning, and they're there at the end, and they're just watching. For this state of chemistry, they're just watching. when you get into more advanced chemistry, you'll notice that they do stuff, and it does influence the reaction. But for this state, pretend they do nothing, they're just watching, they're spectators. We cancel them out to get the net ionic equation.